All right, so this is a little bit of an extra topic. There's kind of a lot of good places after the first things to put this. This is kind of a really neat application of least squares, or not of least squares, of linear algebra. That's called least squares. So sometimes when we're solving a problem, sometimes we're going to get no solution for a system of equations. Sometimes we don't need an exact solution, though. Sometimes we just need to have an approximate solution. And so there's a lot of variety of techniques for trying to find an approximate solution. One of the most common is least squares. So before we get into what least squares is and how linear algebra works with that, we've got some other linear algebra definitions we need to throw in here. So start with the first one. The transpose of a matrix A transpose, is the matrix whose columns are formed from the corresponding rows of A. That is to say that the rows of A are going to become the columns of A transpose. So if we have a matrix A, which is A, B, C, D, E, F, then A transpose, the first column will become the first row of A. So it'll be A, B, C, and then the second column of A transpose will become the second row of A. So D, E, F. So if the dimensions for A are n by m, A transpose has dimensions m by n. So it's an m by n matrix. If you're trying to type this in octave, typically we'll write A and then the little apostrophe symbol. So that's how we could write it in octave. And then a symmetric matrix is a matrix A such that A transpose equals A. So it's equal to its own transpose. This will come up a little bit when we see least squares. We'll see a lot of symmetric matrices. Continuing on with some of these extra definitions that'll help us. The inner product or dot product between two vectors u and v in Rn, denoted u dot v, is the product u transpose dot v. So u dot v is the same as u transpose dot v. Essentially the idea here is we're taking u1, u2, u3, however long we have. In this example, we're just going to go through u1 through u3, and then v1, v2, and v3. And if we were doing this multiplication, what we would get is u1 v1 plus u2 v2 plus u3 v3. Now notice that if we were actually doing this as a matrix, this should be a 1 by 1 matrix, but when we're talking specifically about the inner product or the dot product, we're saying that this ends up becoming a scalar instead. So we don't have a matrix anymore, this is a scalar output. So let's say we wanted to go ahead and determine u dot v, v dot u, and v dot v between these two vectors. If you think you've got it from the example, give it a try and then take a look at what we got. Otherwise, you can kind of see the first one or two and then give it another shot. So u dot v will equal 1 times 3 plus 0 times negative 1 plus negative 2 times 1. Typo there, which will be 3 plus 0 minus 2, which is 1. If we wanted to find v dot u, well, this should just be the same thing, because all we're doing is taking the same entries and we're just multiplying them in a different order. So we're taking 3 times 1 plus negative 1 times 0 plus 1 times negative 2, and we should get, again, 1. So these two ought to be the same. And then last, if we're taking v dotted with itself, well, that means we'll take 3 times 3 plus negative 1 times negative 1 plus 1 times 1. What you might notice is that this is 3 squared plus negative 1 squared plus 1 squared, and this gives us 11. Okay, so there's an example then of a couple examples of the dot product. So if we want to go ahead to a different terminology that uses the dot product, say we have the length or norm of a vector. This is defined as being the square root of a vector dotted with itself. So from the previous example, I believe that's 3.2, the length of v is just the square root of v dotted with itself, and from that example, then we would say the length is the square root of 11. Given that we have two vectors u and v, we define the distance between u and v as the length of the vector u minus v. So we'll take whatever the length is of u minus v, or in other words, the square root of u minus v dotted with u minus v. So notice that there are going to be many different ways for us to define distances and norms. In our class, we're going to use something called the standard Euclidean norm. So this is the norm we're going to be using. The only reason you need to know this name is just in case you see another class in the future that uses a different norm, you kind of know where this is coming from. Alright, so let's say we want to find the distance between those two vectors we had from before. So we want the length of u minus v. So that's the square root of u minus v dotted with u minus v. And so that'll then become the square root of 1 minus 3 is negative 2, so negative 2 squared, plus 1 minus negative 1 is 1, so plus 1 squared, and then plus negative 2 minus 1 is negative 3, so negative 3 squared. So we have the square root of 4 plus 1 plus 9, and so that's just going to be the square root of 14. Alright, so you'll want to have all those definitions kind of handy in your back pocket as we're thinking about what's going on here with least squares. So sometimes instead of just solving ax equals b, which is what we've been doing in this class, we want to just get the best approximation for solving it. And the way to figure out what the best approximation is going to be is to try to minimize our distance between ax and b. In other words, our goal is going to be to minimize the length of x minus b. So then, given our matrix A and our solution vector b, a least squares solution of ax equals b is going to be some x. In other words, what we're saying is the least squares solution is going to be the one that is the smallest of these possible distances. And so there's a theorem that has a proof that uses a bunch of theory we don't know yet that says the set of least squares solutions of ax equals b coincides with the non-empty set of solutions to the normal equation A transpose ax equals A transpose b. So in other words, normally we're trying to solve A augmented with B in a matrix, and we get the reduced row echelon form, and that gives us what our answer is. If we're trying to get a least squares approximation, we're to take whatever the A was, take the transpose of that, and multiply it by A, and then augment that with what we get when we transpose A and multiply it by that solution part B. So let's say we want to find the least squares solution for this A and this B. So normally we would want to go ahead and put, so normally we would do A augmented with B, and we would do 2, 1, 1, negative 2, 0, negative 1, 2, 3, 0. So if we take this system and put it into our calculator, we get a 3 by 3, so we have 2, 1, 1, negative 2, 0, negative 1, 2, 3, 0. If we get the reduced row echelon form of that, what you'll see is we end up getting no solution. 1, 0, 0, 0, 1, 0. 0, 0, 1. So we get no solution. So in order to approximate and try to get some sort of approximation, we'll do least squares. And so first we need to find A transpose A, and we need to find A transpose B. So let's put these two into our calculator so that way we can do it a little bit quicker. I'm sure you guys know how to do matrix multiplication. So we've got a 3 by 2. So this will be kind of our quick way of doing it. So we've got 2, 1, negative 2, 0, 2, 3. And then our matrix B is going to be a 3 by 1 with entries of 1, negative 1, and 0. And so when we go to find A transpose A, we'll end up getting 12, 8, 8, 10. Now notice if you're doing this by hand, when you do A transpose A, you get a symmetric matrix. We talked about symmetric before, so this can be a double check to make sure you did properly do A transpose A, especially if you're doing it by hand. And then we also want to find A transpose B. Whoop, added a parenthesis I didn't need. And so that'll get us 4, 1. And so here what we're saying is we're trying to solve the equation A transpose A x tilde equals A transpose B. So in other words, we're taking 12, 8, 8, 10 times whatever x tilde is, and we're supposed to get 4, 1 as a result. And so if we want to solve this, we'll put it into a matrix. So we get 12, 8, 4, 8, 10, 1, and we'll get the reduced row echelon form of that matrix. So 1, 0, 4 sevenths, 0, 1, negative 5 14ths. And so that tells us then that x tilde, our approximated answer, is going to be 4 sevenths, negative 5 14ths. So just to verify that we understand what's happening here, let's say I wanted to go ahead and put in this x tilde. So it's a 2 by 1, and its entries are 4 sevenths and negative 5 14ths. If we take A times this x tilde, we get this matrix. Let's see what we get. 11 14ths, negative 8 sevenths, and 1 14th. And so when we look, this is as close as we could get to what B is. And so let's actually take this and subtract B. So if you notice, we don't end up getting an exact answer for any of these things, but they're as close as we can get to getting the exact answer. So this is going to be our least squares solution, our best approximation as to what we should get. Now there's a lot of places where we'd want to use least squares. One such example is going to be with linear modeling. So one of the main problems that we have as mathematicians, scientists, and statisticians is trying to analyze and understand our relationships that we have between variables when we're looking at data sets. In calculus, we're often given functions to analyze and use. Unfortunately, in the real world, we often have to build or create the function or formula on our own to describe our data. And so the good news is that linear algebra and this method of least squares can kind of help us. So suppose that we collect data on age versus brain mass using this information in the table down here, and we want to see if it can help us hypothesize what's happening to brain mass after the age of 45. So kind of taking a look at this, it almost looks like I could draw some sort of line that would be very close to estimating this relationship. And so maybe when we want to hypothesize that our brain mass decreases linearly with age. What this means is we're going to try to find a function that is linear. In this case, our cx plus a equals f of x. And we want to use this in order to try to determine if we actually have the relationship. So if we do have this relationship, we'd want to know what our values for c and a are that would best fit what our data is. So that's what we're going to try to do, is we're going to try to find a best fit line in order to predict the brain size for, say, a 90-year-old. So when we say best fit line, what you should read is use least squares. So least squares to be what we use to try to find a best fit or an approximation. And so when we're looking here at this table, our age is going to be our x, and our brain mass is going to be our f of x. So this will give us a system of equations that we can use. So we should get as our equations, if x is 45 and f of x is 4, we should get the equation 45c plus a equals 4. We should also get the equation 55c plus a equals 3.8. 65c plus a equals 3.75. 75c plus a equals 3.5, and 85c plus a equals 3.3. Now normally we would go ahead and take the coefficients over on the left, put them into a matrix, and we'd take the constants on the right, put them on the other side of the augment line, and that would give us what our system of equations would be. But notice that we're not going to end up, if we try to do this, getting a solution. So we get our coefficients for c, our coefficients for a, and then the constant portion. So we'd get 45, 1, 4, 55, 1, 3.8, 65, 1, 3.75, 75, 1, 3.5, and 85, 1, 3.3. And so remember that this is what our big matrix A augmented with B looks like. And we're trying to figure out what C and A are going to end up being. So if we did get the reduced row echelon form of this, I'm not going to show you, but we will end up getting no solution here. And so least squares says that we want to do A transpose AX and set it equal to A transpose B. And so here X is whatever vector it is we're looking at. In this case, this X vector is going to be C and A, whatever those values are that we're trying to predict for them. So it gets very tricky here when we start using the nomenclature. So kind of keep in mind this X here is referring to what the years we have of the age of the person that we have our data from, and this X tilde here is a vector that holds what our values for C and A are going to be. So let's get this A transpose A and A transpose B. If we find A transpose A, what we'll end up finding is that we'll get the matrix 22,125, 325, 325, and 5. And for A transpose B, we should get 1175.75 and 18.35. And so if we go to put this into a matrix, and get the reduced row echelon form, what we should get is something that looks approximately like this. And so what this tells us then is that we should have C be approximately negative 0.017, and A should approximately be 4.775. A little bit of rounding there, I believe, when we did this reduced row echelon form. And so our function is going to be f of x equals negative 0.017x plus 4.775. And so let's say we wanted to predict the brain size of a 90-year-old. What that means then is we're taking f of 90, which would be negative 0.017 times 90 plus 4.775. So negative 0.17 times 90 plus 4.775, and we should get 3.245. So this is what we would expect the brain mass of a 90-year-old individual to be in pounds based on the equation we came up with. So this is one of the ways that we can go ahead and set up a function and create and figure out what it should be and what it should look like based on least squares. This will give us a best fit line. Now you might be wondering, are lines the only thing that we can get a best fit of? And the answer is no. For any n-degree polynomial, we could go ahead and set up a system of equations for whatever that was. So let's say we wanted to go ahead and set it up for a quadratic function. So right now we're just going to do the setup. I'm not going to go ahead and solve all the way through, although I definitely recommend trying to solve all the way through and putting that on the discussion board. So here, if we're talking about a quadratic function, what we're really saying is we want to figure out what ax squared plus bx plus c function will be y. And so in this case, the x squared and the x and the 1 are going to be the things that are in front of our variables, which are a, b, and c. We want to find what a, b, and c are. There are real unknowns. And we'll use this data to set up our system of equations. And so here, the first equation will be a times 0 squared plus b times 0 plus c equals 1. We'll get a times 1 squared plus b times 1 plus c equals 3. We'll get a times 2 squared plus b times 2 plus c equals 6. And we'll get a times 3 squared plus b times 3 plus c equals 12. And so here, if we're setting up our A matrix and our B matrix, our A matrix will be 0, 0, 1, 1, 1, 1, 4, 2, 1, and 9, 3, 1. And so remember, this is going to be the coefficients for the A, the B, and the C. So notice that here, with C having just being by itself, we can assume its coefficient is 1. And so on the other portion here, the B vector is going to be 1, 3, 6, 12. Again, don't confuse this B vector that we kind of used in all of our notation up until this point with this B over here. There's a little bit of notational abuse that we want to kind of be careful of. So remember, you'd be trying to solve the system of A transpose A, x equals A transpose B, and I want to give you guys what the final least squares solution is. so that way you can try to verify that you can do this. So we should get x squared, y equals x squared plus 0.6x plus 1.1. So this should be our final answer for our least squares solution. You still have some steps to do. You want to find A transpose A, you want to find A transpose X, you want to put them in, or transpose B, you want to put them in a matrix and then get it into the reduced row echelon form. So we've got one more type of function we can try to approximate before we kind of talk about another cool least squares trick we can do in the lab. So we can extend this to functions that aren't polynomials. So in fact, there's a bunch of functions that are approximated by linear combinations of sine and cosine. So these give us examples in which our function is a trigonometric polynomial, which show up in something called Fourier series, which is way beyond what we're going to be doing in this class, but maybe you might see it in a physics course. So a certain experiment is going to produce the data 0, 7.9, pi over 2, 5.4, and pi, negative 0.9. We want to find values for A and B that describe the model that produces a least squares fit of the points by a function of this form. So in other words, what we're going to be doing is the same thing we've been doing, is we'll plug in the x for the x part, and we'll plug in this for the f of x part. So for our first equation, we should get A cosine of 0 plus B sine of 0 equals 7.9. Our next equation should say A cosine of pi over 2 plus B sine of pi over 2 equals 5.4. And our last equation should say A cosine of pi plus B sine of pi equals negative 0.9. So all we did was we just used each of these data points. And this, leaving the cosines and sines in there, is not something you're going to want to do. You're going to want to simplify that to make it easier to see what your matrices are going to be. So here we'll have the equation A equals 7.9, B equals 5.4, and negative A equals negative 0.9. Now notice that we can tell just from the first line and the last line that we're not going to be able to solve this system and get an answer without doing least squares, right? We're going to have to find a way to get an approximation for this. There will be no solution to this system otherwise. So here, we're going to use our matrix A. So note this is the matrix, not the variable. And so this will just come from taking the coefficients for our A and our B. And this will be 1, 0, 0, 1, negative 1, 0. And then our little b here, we'll get just what's on the other side of this, which will be 7.9, 5.4, and negative 0.9. And so A transpose A ends up giving us 2, 0, 0, 1. So again, we get a symmetric matrix when we do that. And A transpose B will get 8.8 and 5.4. And so if we wanted to go ahead and create this system, we'll get 2, 0, 8.8, 0, 1, 5.4. And to do the row reduction here, all we need to do is take row 1 and divide it by 2, and we get 1, 0, 4.4, 0, 1, 5, 4. And so taking this, that means that our least squares approximation for this particular trig function is going to end up being 4.4 cosine of x plus 5.4 sine of x.